All right, good morning. Welcome to my answer key for this week's worksheets. This is 2J. We have a block of mass M's. This is a pretty popular problem. We're going to drag something across the table. You might actually see this in class. It's taking a quick hit from a bat. Its front end is at position XO at time t. It's moving to the right. Really? Okay. The block slides on a rough surface and is also connected to a hanging mass that's pulling it to the left. The front end of the block reaches position D at time t1. The instant the block comes to rest, the block then returns to position x0 at time t0, having a leftward speed of v2 at that time. All right, so forces during from the beginning. So it's smacked and it goes flying across here. So what forces would we have? Well, we would have a force of gravity, free space on bingo. There's also the table pushing up on the block, which is a normal force. So those are a balance. Those are in equilibrium. Those aren't going to really affect the problem. What else is happening? So we have a rope pulling this way, and since the block is going to the right, friction, it's kind of hard to draw these because they really should both be coming from the same place. Friction is also going to the left. So we have two forces pointing to the left. And then after the block comes to a rest and then starts sliding the other way, how is this different? Well, this part isn't different. It's still the same mass, so it has the same weight. It's still the same normal force. Balancing that, we still have this tension, but now the friction is going this way. All right, so is the magnitude of the acceleration greater before it reaches D or after? So let's see. So the net force here would be, for position 1, would be tension plus friction. Right? So the net force would be tension plus friction, whereas for situation 2, the net force is equal to tension minus friction. So which one's bigger? Well, this one's bigger. Therefore, that acceleration is bigger because the net force is bigger. All right, that's 2.5 minutes. Let's see what else you've got. On the grid below, sketch a graph of the block's velocity as a function of time, taking right to be positive. All right, so it starts off with some big old positive v0 velocity, right? And let's say this is t1. And this is let's say this is T2 here, okay? So things are going to happen here and here. So it's so what's happening is it's slowing down, right? From V0. Do I have a ruler? Yes, I do. So it starts off with some positive velocity because it's going to the right. And then it slows down, and at T1 it stops. So velocity is 0 here. And then, now it's got a leftward velocity, right? But it's slower. Its acceleration is less. So we need to draw a line that's shallower. You see here we have positive velocities, which are slowing down to 0. It gets to point D here, and it stops. Velocity is 0 here. These are positive velocities and negative velocities. Now it's going left, so it's got a negative velocity. The slope of this line is the smaller acceleration. This is the bigger acceleration, as we showed on the last page. We're at about 4 minutes. All right, so what comes next is K. So for K, we have a block is on a rough table, and the block is connected to a string that passes over an ideal pulley. In case 1, the free is connected to a hanging object of 10 kilograms. In case 2, the hanging object is removed and a person grabs a free end and pulls with a constant force of 98. The weight of the hanging object in case 1. In both cases, the block is released from rest the same distance from the right edge of the table. So for block 1, the dots below represent each case. Draw the forces acting on those objects after the system is released. All right, so am I on camera? I've lost my camera. Oh. All right, here we go. So here we have force of gravity and the normal force. And what's happening here is the rope is pulling it this way. Right, that's case 1. All right. Hanging object 2. So this is the free body diagram of the hanging object. So the hanging object is, okay, that makes sense. It's the force of gravity of the hanging object, and then there is the tension pushing up on it. All right, so that is for case 1. That the block accelerates in both cases when the block reaches right edge table in less time in case 2, even though the force is the same. This occurs because there's a different amount of tension in the two cases. Explain why the block reaches the end in less time in case 2. Okay then. In case 2, the acceleration is larger, so it reaches the edge faster in case 1. This happens because the force of tension in case 2 is now 98 newtons, whereas in case 1, the tension is less than 98 newtons. Analyzing the hanging object in case 1, we can see that if the tension were equal to 98, the hanging object would not accelerate downward. So for the hanging object to accelerate downward, the force of tension in case 1 must be less than 98. All right, so here, if we could figure out actually what the tension is equal to here, right? There's an acceleration. The mass of the system would be m plus 1 times the acceleration is equal to the net force, which is tension minus mg. And over here, the net force is just equal to 98, which is equal to m times the big M times the acceleration. So you can see we have more mass involved here on this side. In this situation, we have the mass of both of them, which is slowing it down, right? And here we just have the mass of this. This is a pure force here pulling it down. All right then. Okay, we're at 7 minutes. Let's finish this up. Okay, I just did that actually. I just talked about that. In the systems, one has 2 masses, the other one has 1 mass, and that's why. All right, let's stop this video.